Welcome back. In today's video, we're going to discuss Henry's Law, or gas solubility. This is a topic that's going to allow us to bridge the gap between our gas law unit and our solubility unit. We're going to see another gas law proportion that's very helpful. First of all, let's discuss the solubility of gases. We recently had a lesson on reading solubility curves, and we looked mostly at ionic compounds and their solubility in water. And we saw that most of the time, as temperature increased, the solubility of ionic compounds would increase as well. So that was a direct relationship. For gases, though, that's not the case. Gases actually do not like warmer solvents. So there's an inverse proportion, as you can see in the graph on the right-hand side of the screen. No matter what the gas is, the solubility decreases with temperature. And let's go ahead and acknowledge the fact that helium has a very small slope. But frankly, helium's not very soluble in anything under any conditions anyway, because it's like the most nonpolar thing we have. So that explains that. Why is that, though? Why do you think gases don't like temperature to become soluble? Well, think about what dissolving is. It's the interaction, the intermolecular forces of the interactions between water molecules and the solute molecules, which in this case would be gases. Most gases have very small intermolecular forces. That's why they're gas in the first place. If they had strong IMFs, they'd be liquids or solids. And we know that gases already have quite a high kinetic energy compared to the particles of the other states. So as you increase the temperature, gas particles move faster, which means their kinetic energy is just too much for the IMF interactions between that molecule and the water. So it's real easy to send gases away from the solvent, or water, or whatever the solvent is. So we have an inverse relationship. But temperature isn't the only thing that affects solubility, especially for gases. Another factor that's very important for gases is pressure. This is the idea behind your sodas and carbonated beverages. That's why those bottles are kept under high pressure. If you ever try to squeeze an unopened bottle of soda, it's very difficult. They're pressurized. In essence, what pressure does is force the gas particles to stay in solution because they have less freedom on the outside. It's actually better for them to go be under the intermolecular interactions with water than to be crowded in the space quote-unquote free. So in this other, on the bottom left-hand side of your screen, you see a direct relationship between solubility and pressure. So as we move forward with Henry's Law, we're going to be talking about this direct proportion. But let me point out before we move any further that these straight lines that you see in this bottom left-hand graph, those are only straight if the temperature is held constant. If the temperature is not held constant, you're going to see a curve. And in the real world, that's the case. But the drawback to that is when you're varying temperature and pressure, you have to use more higher level math to negotiate the problem. So for us, we're going to assume in these problems that temperature is held constant, so we have a nice linear direct relationship. In this picture, let's focus on the bottom of the picture first. And let me kind of explain what pressure does. So you see here we have a mixture of CO2 and water. Water is the solvent, CO2 is the gas, the solute that's trying to be dissolved. Normally CO2 has a relatively weak interaction with water. You can see here there are two molecules quote-unquote dissolved, and there's a bunch in the headspace. So let's double the pressure. And what's happened here is we've doubled the number of particles, of the CO2 particles in the headspace. And look, we were able to double from 2 to 4 the ones that were dissolved in water. If we double that pressure again, then we are also going to double again, and now we have 8 CO2 molecules dissolved in the water. That's the direct proportion of this. And now you can see better what I said on the previous slide about how the CO2 molecules actually have more freedom being in the solution, interacting with the water, than up here in this crowded space now. Going back to the top of the picture, you can see what we call the Henry's Law relationship. It's just another direct proportion. This has the same form as y equals mx from algebra. It's another straight line, and the slope of the intercept would be 0. So S is the symbol we're going to give to solubility. G is just for the gas. The P over here is the partial pressure. Remember back in the gas law unit, we learned about Dalton's law of partial pressures for gas mixtures. These are mixtures because we have two different substances, the solvent and the solute. So we're dealing with the partial pressure of the gas. And Henry's law would still apply if we had more than one gas here. You could do the solubility of each gas individually according to Dalton's law. And then K is a proportionality constant we call the Henry's law constant. It's just the slope of those lines that I showed you on this previous slide. So here are some typical Henry law constants for some gases that we saw on that very first page. They're usually pretty small. We have negative exponents. They won't all be negative exponents because some gases, if they're more polar, will interact strongly with water. An example would be ammonia. I'm pretty sure ammonia has a positive exponent because ammonia is very soluble in water. Well, let me ask you, why are some of these gases more soluble than others? So from these four right here, helium, oxygen, nitrogen, CO2, which gas is more soluble in water? If you said CO2, you're right. Now, can you tell me why? The answer is due to intermolecular forces. All four of these gases are nonpolar, but with increasing mass, we have increasing London dispersion forces. CO2 here has the greatest number of London dispersion forces, so it will be more soluble in water than these four. That's why I was talking about if I saw ammonia here, ammonia would be able to hydrogen bond with water, and that's why its exponent would actually be positive, and we would see a very, very steep slope for the solubility of ammonia in water. Now, because we do have a proportionality constant, we can actually turn Henry's law into another proportion like the other gas laws, such as Charles and Gay-Lussac, and all the other ones that are direct proportions. If the solubility goes up, then the pressure will go up. Very straightforward. So now let's do some example problems. All right, here's some practice problems. And number one, if 27 grams of acetylene dissolves in 1 liter of acetone, so acetylene is the solute, acetone is the solvent, at 1 atmosphere pressure, what is the Henry's law constant? All right, well, we know that solubility is equal to Kp. So if we want to know what K is, it's going to be S over P. Solubility is a term that quantifies how much of a solute is dissolvable in water. So typical units for solubility are in grams per liter. You could also have moles per liter. That's a molarity, also called a molar solubility. We'll talk more about those terms in AP chemistry, but for now, it's good for us to know that solubility is grams per liter. So for this problem, we have 27 grams divided by 1 liter, and then let's divide that by the partial pressure, which is 1 atmosphere. So for this problem, or for this gas solvent combination, K is 27 grams per liter atmosphere. Not the hardest math in the world. In part B, what is the solubility in acetone, so the same solvent, if the partial pressure is 12.5? Well, now that we know K, we just plug it in, 27 grams per liter atmosphere. Now the pressure is 12.5. See how the atmospheres cancel? So the solubility is going to be 340 grams per liter. In number 2, the solubility of carbon dioxide in water is given here. This is another way to express the units per 100. We saw this on the solubility curves. In a partial pressure CO2 of, that's the pressure given there. What partial pressure CO2 is necessary in a soft drink canning process in order to allow the solubility of CO2 to equal 0.886? So there's a couple different ways we can work this. If we realize that, or we utilize K here, knowing that K is always constant, we can actually use S1 over P1 equals S2 over P2. If we set that up, the initial solubility is 0.161. I'm going to drop the units for now. At 760 millimeters of mercury. And I want the solubility for my soft drink to be all the way up at 0.886. So what pressure will I need? I did the calculation. I think I rounded it correctly. And I got 4,180 millimeters of mercury. That's about 5.5 atmospheres, to give you a little bit of perspective. Let's do one more of those together. You can hit pause and try number 3, and then I'll work it for you. Calculate the solubility of carbon dioxide in water at 0 Celsius and a pressure of 3 atmospheres. The solubility of carbon dioxide is 0.348 at 0 Celsius and 1 atmosphere. Well, we can use our same S1 over P1 equals S2 over P2. And for this problem, we're looking for S1. So S1 is going to equal S2 times P1 over P2. And that will equal 0.348 times the 3 atmospheres over the 1 atmosphere. That's a terrible 1 atmosphere. So we simplify that down, keeping in mind what our units are going to be here. Solubility is 1.04 grams per 100 mils. All right, hit pause now and try 4, 5, and 6. I'll come back in a moment with the answers posted. All right, well, here are the answers to 4 and 5. They're pretty straightforward. Hope you got 1.2 grams per liter and 23 atmospheres. Number 6 was just a little bit different. It went back to using the S equals KP relationship. And if you just plugged in, you got S to equal 0.00276 moles per liter. And if you were a little unsure about how to go to grams, it's just a mole conversion. And we're dealing with oxygen, so it's, for oxygen, 32 grams per mole. So therefore the final unit worked out to be 0.0883 grams per liter. If you have any questions about any of those, come and see me.